Hello and welcome to this section of the Circuit Analysis Tutor. In this section we're finally going to begin to tackle one of the most central topics that you'll learn in a first semester engineering circuit analysis course, and that is the topic of Thevenin equivalent circuits. It is a big deal, right? And I think you'll see in just a few seconds, even before we do a problem, why it's such a big deal. But basically a Thevenin equivalent circuit is going to let you simplify circuits so much that every student has to learn them, and not only learn them, but master them. Now, you probably already noticed, if you've looked in your textbook, that after Thevenin equivalent circuits, there's another topic called Norton equivalent circuits. We're going to cover those in a little bit. What you're going to find, though, is that the Norton equivalent circuit is super easy to find once you understand what a Thevenin equivalent circuit is. So it looks like we have lots of different kinds of topics, but Norton equivalent circuits, it's almost like an add-on. Once you understand Thevenin, Norton just kind of naturally follows. All right, so up until this point, just kind of take stock of where we've been in circuit analysis. We've learned the basics of power and current and resistance, and we've tackled Kirchhoff's voltage laws and current laws, which are always true. And then we've tackled node voltage and mesh current, which, if you think about it, really are just Kirchhoff's laws in a slightly different way to make the equations a little bit more rock solid to be able to write them. All right, and then we've learned recently about source transformations, where when you have a big circuit and you have a source, which is maybe like a voltage source in series with a resistance, we can transform that voltage source into a current source. Or if we already have a current source, you can transform the current source into a voltage source. So there's kind of a duality, right? We learned how to flip-flop back and forth between current sources and voltage sources, right? And so those source transformations that we did recently, we're really just zooming in to the left-hand side of the circuit, usually, where the source lies. The Thevenin equivalent circuit is much more general, and I'm going to say it a couple of times, and I'm going to draw it on the board to show you. A Thevenin equivalent circuit lets you take your entire circuit that you have and basically model it as a voltage source and a resistance, right? Not just a part of the circuit, not just the part that deals with the source. I'm saying the whole enchilada. Right? Let me show you what I'm talking about. Let's just say that I have a circuit. Now, I'm not going to draw a circuit. I'm writing the word circuit here because I'm going to put it inside of a black box. Now, you don't know what's in here. This could be 15 current sources in there and 29 resistors. Could be 34 resistors and 3 current sources and 2 voltage sources, all interconnected in weird ways. Okay? But the only thing you know is that coming on the outside of this box is 2 little holes. One wire is terminal A and one wire is terminal B. That's all you know. You cannot see what's inside the box. You don't even know what's inside the box, right? What the Thevenin equivalent theorem says is that I can replace this. So I'm going to kind of draw a little arrow like this. I can replace this. Doesn't matter what's in the box. I can replace the whole enchilada with the following. With a voltage source that I call the Thevenin voltage source, VTH, the Thevenin source. It's just a voltage source, in series with a Thevenin resistance. And this guy I'm going to label terminal A, and this guy I'm going to label terminal B, right? So if you think about it and you can compare this drawing to this drawing, really, the black box that we drew is kind of like here. You kind of go around like this. Right. So in your original drawing, I have lots of stuff. I have, resistors and current sources and voltage sources. It doesn't matter. For the purposes of electric circuits, all you really care about is how does it behave in terms of terminals A and B. If I hook a meter up to terminal A and B, what's it going to look like? If I hook terminal A and B up to a motor, or if I hook terminal A and B up to a computer, or whatever I'm trying to build, right? If the terminal behavior between this equivalent circuit and whatever's inside of here, if the behavior between terminals A and B is the same, then they might as well be the same. I mean, inside the box. It doesn't matter. It's a black box. It just matters how terminals A and B behave. And what the Thevenin theorem really says is that any network of resistors and sources of any type, right, can always be rewritten in terms of a single voltage source and a single resistance. And when you think about it, that is crazy that you can do that. that I can have 39, they don't have to be nice behaved, well-behaved circuits, 39 current sources all connected in crisscross, spaghetti network inside, and lots of resistors going everywhere, right? It may be hard to analyze, but any resistive network like that can always be rewritten in terms of a single resistor and a single source. That's pretty darn amazing, right? And I'll give you a little kind of foreshadowing, we're going to get to this later, when we get to AC, to alternating current, and when we have inductors and when we have capacitors, in addition to our resistors, the Thevenin theorem is going to hold. This box really can contain inductors and capacitors and all kinds of other things too, and we're still going to be able to write a simplified circuit. The simplified circuit is going to look slightly different, but it's going to be super, super simple, and it's going to be able to model what's in that box precisely, right? So you can see why this is so powerful, because if you have a very large circuit, with lots of branches and nodes and everything, I mean, we can just analyze that, but if we just take the time to find the Thevenin equivalent circuit, then it might make a whole lot of sense just to work with that Thevenin equivalent circuit. Why not, right? If it's the same behavior, why don't we just build the simpler circuit instead of building the complicated circuit, right? So that's really the power of it. So the question is, how do you transform, so to speak, from this complicated network of whatever it is in here to the Thevenin equivalent circuit? How do you do that? Okay, so let me go ahead and at least write it down. Okay. Thevenin equivalent. Okay, there's two things you need to find. You need to be able to calculate the Thevenin equivalent voltage, and you need to be able to calculate the Thevenin equivalent resistance, equivalent to what's in the box, basically. All right, so don't forget, when you're talking about Thevenin equivalence, you always have to have two terminals identified. You always have to have two terminals identified because those are the two terminals through which you're kind of viewing the world and modeling what lies beyond them, right? So whatever the circuit is, you have to have two terminals you're looking at so you can kind of look and see how the sources are behaving inside of there. In other words, the Thevenin equivalent circuit is going to be different depending on which terminals you're probably looking at, right? So you have to make sure you're looking at the right terminals in the problem. The problem is going to always tell you, find the Thevenin equivalent circuit from terminals A and B perspective, or from the point of view of these two terminals A and B, right? So to find the Thevenin equivalent voltage, this is what you do. You find open circuit voltage between, that's what BET means, terminals A and B. It's as simple as that, right? In other words, there's a complicated network in here. I've tapped off two terminals. If I put a voltmeter here, a regular voltmeter, I'm going to measure some voltage, right? When I say open circuit voltage, I mean I don't connect any load here. I don't put any resistors or anything in between terminals A and B. I just simply measure the voltage. The voltage that lies between A and B without connecting a load or anything in the way. Whatever that voltage is, that's the Thevenin equivalent voltage. And I'll show you how to calculate that in a second. All right, it's going to be different for every circuit, but there's a methodology to figure out how to calculate the Thevenin equivalent voltage. Once you have it, you already know half the answer because you know what the source is going to be. All right, to find the Thevenin equivalent resistance, RTH, you have to find the short circuit current between terminals A and B. Then the equivalent resistance, the Thevenin equivalent resistance, is the Thevenin that you calculated in step 1 divided by I, short circuit, SC. You might want to get used to reading this. Most books abbreviate it this way. The TH means the equivalent, Thevenin equivalent. The ISC means the short circuit current. So when you go back and you look to our drawing, to find the Thevenin equivalent voltage, you just measure the voltage between the two, and we'll show you how to do that. To find the Thevenin equivalent resistance from terminal A and B, you have to place a short circuit between A and B and measure the current really we're calculating the current, but if you're in the lab, you'd be measuring the current between A and B. Once you short circuit those terminals together, figure out how much current's flowing through A and B, or across A and B, when you short circuit those terminals, and then you plug it into here. This is just Ohm's law again, restated. V is equal to IR, right? So I'm just solving for R. It's equal to the Thevenin equivalent voltage divided by the short circuit current that we measured or calculated. So this is really it. I mean, you can summarize Thevenin equivalent with two rules on the board, right? Now the trick is, this is where, people start to have problems in circuit theory, right? A lot of times. Because it looks simple to find the open circuit voltage between A and B. How do you think you're going to do that? Well, you're probably going to use node voltage methods, or you're probably going to use mesh current methods to figure out what the voltage is across A and B. So if you're weak on mesh currents, or if you're weak on Kirchhoff's laws, or if you never learned how to write equations properly in a circuit, then the sign conventions will screw you up and you'll never be able to find the Thevenin voltage. And if you can't find the Thevenin voltage, you'll never be able to find the Thevenin resistance because it depends on the Thevenin voltage. And finding this short circuit current, by the way, is going to be the same deal. You're going to need to be able to calculate that using these other techniques that we've learned. So everything builds, just like algebra, geometry, or anything else. You have to learn node voltage mesh current in order to be able to do anything else. But once you know that stuff, the whole world opens to you, because then you'll be able to find these Thevenin equivalents. When we get to AC circuits, I'll show you methods to find those that aren't going to be very hard, and you're going to have to know mesh currents and node voltages and so on. So let's erase this board. We'll put our first problem up, and I think you'll see that it's not that big of a deal to calculate the Thevenin equivalent circuit. And I think you'll actually find it a little bit fun, because you'll be able to take these large problems that we have for you, and you'll be able to simplify them literally into a single voltage source with a single resistor. And if you put both of these circuits, the complicated circuit that you start with and the Thevenin equivalent circuit, if you put them in different black boxes and shuffle them around, and I ask you which one is the Thevenin equivalent and which one's the complicated circuit, you would not be able to tell, because all you have is two terminals. So you'd get your meter out, you'd measure voltage, you'd measure some voltage, both cases would be the same. You would short circuit it and try to find the current that's going through there, and it would be the same current. You could connect different resistors across there. You could put anything you want across A and B. There's always going to be the same terminal voltage and the same current flowing through any load that you connect between these two circuits, because they're equivalent to one another.